Okay, I think we'll go ahead and get started here. It's a pleasure again to have a chance to introduce Gabrielse from Harvard for the Physics Colloquium today. Some of you may have been here last night and heard his public talk on tracking antimatter. And today he's going to focus on more of the technical details, the underlying physics. Many of you know Professor Gabrielse is a world leader in low energy fundamental physics tests of the simplest particles, electron, proton, antiproton, positron, and making tests of quantum electrodynamics. In fact, if you look at his record of what he's done, he has, I think, maybe the most precise measurement of fine structure constant, the G-2 of the electron, proton magnetic moment, very impressive results. And these are often measured on single particles with very high precision measurements, and not just precision, it's accurate measurements where people can go back and check the actual numbers later. That's a much harder job than the precise measurement. So let's see, he got his undergraduate degree at Calvin College, grade school for undergraduate physics, graduate degree at the University of Chicago. When he was a postdoc and tenure track professor at the University of Washington, moved to Harvard in 1987, where he's built up a world-leading program. And today we get a chance to hear of the highest precision measurements in tests of QED. You may have heard that Professor Gabrielse is going to be moving over the next couple of years to Northwestern, where he's setting up a new center of fundamental physics at low energy, looking to growth in that field. So please join me in welcoming Professor Gabrielse.
Well, it's an honor to be back here. I had a great day or two. I even met a number of students to whom I taught quantum mechanics, and all of them told me, maybe they were just being polite, that I hadn't taught them anything wrong that they knew of. So that was that's always a relief. And as Leo said, I am moving from Harvard to start a Center for Fundamental Physics at Low Energy at Northwestern. Given that I've taught some fraction of the students here quantum mechanics and other courses, I'm hoping you might reciprocate by sending me some good students, okay, over the next few years, especially if they're tenacious and very skilled, and don't break more than $2,000 worth of apparatus per week, and things like that. So those are the main characteristics. The topic today is the highest precision probes of the Standard Model and beyond, and I'm really going to focus on two different experiments. To introduce those, both of the experiments I'll focus on will involve using the electron for fundamental physics. Now, the basic idea of the kind of physics that I like to do and the kind of physics that my new center is going to specialize in and hopefully succeed at is investigating fundamental physics. And I know the word fundamental is a little bit controversial because we live in a world where there seems to be effective field theory, and there's all sorts of energy and distance scales under which you're fundamental. But what I meant by that is fundamental in the sense we're really looking for the simplest possible foundation for all of physics. And it's 60 years, a little more now, since the discovery of parity violation. You can't help, if you're doing this sort of physics, to be inspired by the experiment of Madame Wu and the proposal of Li and Yang, of course, that parity violation hadn't really been looked for. And the kind of things that we hope to do in the center are basically those sorts of things. I've said what's here on the top, so let me just point out, we're looking for new faculty members now and postdocs and graduate students. New faculty members, they need to promise to do Wu-like experiments, okay? The new postdocs, they don't have to make such a strong promise. They only need to promise that they aspire to do Wu-like experiments. And the graduate students need to desire a Wu-like adventure, even if they're, determined to get rich in their later life, okay? And so I hope to get some people from here. All right, this is low energy particle physics, and if you think about the orders of magnitude of energy, the LHC, which is the big machine these days at CERN, is up here in the 10 TeV and a little above range. Okay, and every tick mark here is an order of magnitude in energy, and we're doing fundamental physics down here. Last night I told you about setting traps for antiprotons, positrons, protons, antihydrogen atoms. That's all done sort of in this range, and now we're going to go down a little further. Okay, down to cryogenic temperatures, but with a dilution refrigerator, down to 100 millikelvin today. Okay, so that for those of you, I see some of you that I know aren't physicists in the audience who came back from last night, that's just 1/10 of a degree above absolute zero. Okay, that's pretty cold. All right. Now, the standard model, in physics we always talk about the standard model. It's not the most inspired name we've ever come up with, but then we have quantum numbers of truth and beauty and other things that maybe could have been improved on. But the standard model is, I'll say more about it in a moment. I like to call it the great triumph, but also the great frustration of modern physics. Now, what is the standard model? The standard model is basically a collection of particles, okay, and it's some interactions between these particles, some symmetries of these particles, and then you wrap it all up in quantum field theory, okay, and quantum field theory generates some symmetries as well. And the standard model has been very flexible over the years. For example, we added the Kobayashi-Maskawa matrix at one point, right? Just added another matrix, sort of tacked it on the outside, and said, okay, it all fits in the standard model. Well, that's just because we made the standard model a little bigger. So the standard model is like a dirty snowball, and everybody packs their piece of snow in there, and as long as it all works. But at least for some of our taste, it has an awful lot of parameters in it. Okay, now that doesn't say maybe reality does have that many parameters, but there's quite a lot. And we've tried efforts to unify some of these forces, which many of you know about in more detail than I. They've resisted the efforts of the physics community in some sense. So we get the impression that maybe this isn't complete. And then as I noted last night, there's other reasons to know it's not complete. Now, the question is, the standard model, is it right? Okay, and in science, unlike perhaps in the humanities, we actually have a doctrine of right and wrong. Okay, we can ask a question, is it right and is it wrong? You can't ask if someone's novel is right or wrong typically, so it's a little different. Okay, but we test its predictions, and the low energy methods are the most precise. We test its symmetries. The low energy methods are the most precise. We look for new particles. That's where clearly the advantage goes to high energy experiments, okay, where you crash things together and you see what comes out. That's being done very effectively right now at CERN. And basically we're interested, can it predict the universe that we observe? Because in physics, we never, as you all know, we never prove that something is right. We only fail to disprove it after a certain number of experiments. And if we do that, if we fail to disprove it enough, then eventually the community decides, and it's interesting sociology, but then we adopt whatever paradigm this theory is describing. That's the standard model right now. Now, the first part of my talk is what I'll call the greatest triumph of the standard model. Now, my own point of view comes into that, of course, but I'll explain why at least that's a defensible statement. And what I'll be talking about is a magnetic moment. And so the first thing I'm going to do is say, well, what is a magnetic moment and what is its natural scale? So this is the only derivation that we'll do today, at least I think. And so let's make a magnetic moment, and we'll do a little more than dimensional analysis to see what size it is. So let's take a particle, charge E and mass m. Let that particle go round and round in a circle, so it'll have some velocity, which can be written as an angular velocity omega times the radius, and it's a radius. Okay, so that's pretty simple, basic freshman physics. Now, circular motion, if it has one quantum of angular momentum, okay, the angular momentum then, L, would be m times omega times r in terms of these quantities. And if it's one quantum in quantum mechanics, we would set that equal to h bar, because h bar is the unit, the basic unit, the quantum of angular momentum. Okay, now if we put this together, we can write that a magnetic moment, which in SI units is the current times an area, we can write down what the magnetic moment is here in some detail. Okay, this current is pretty easy because there's one elementary charge going around once per revolution period. Okay, so here's the element, current is charge per time. Okay, the charge is E, and the time is 1 revolution period, which is 2 pi over omega. And then we multiply by the area, which is pi r squared. Okay, so it's not such a hard derivation. We clear the constants and multiply it together. And what we get is that this magnetic moment is the charge times h bar times twice the mass of whatever particle we're dealing with. This means, first of all, that if you have a particle that's heavier, you would naturally expect it to have a smaller magnetic moment. Okay, so when I just briefly mentioned last night that we had measured the magnetic moment of an antiproton and a proton almost 1,000 times more accurately than it, and compared them almost 1,000 times more accurately than had been done before. Since the proton mass and the antiproton mass are 2,000 times bigger than the electron mass, that's a much smaller moment, okay, and that's one of the challenges of that measurement. Okay, for an electron, this particular combination of constants, this natural size magnetic moment, is called the Bohr magneton. Okay, so an electron naturally would have a magnetic moment of a Bohr magneton. Well, but it's really, I should put the sign of a charge here. I was just making the magnitude argument. Since this really, we should have done this with the sign, we would predict that the magnetic moment actually would change sign with the charge. Okay, so a positron and an electron would have an oppositely signed magnetic moment. Okay, but this is the Bohr magneton. All right. So now let's look at the Standard Model's most precise prediction. Okay, and people often, like Leo did, talk about quantum electrodynamics. I don't like to do it that way, and I'll explain why in these next two slides. Okay, the Standard Model's most precise prediction is of the size of the electron magnetic dipole moment. Okay, and here's the prediction. Well, it's a vector, this magnetic moment, because it's it's a little bar magnet, right? It has a direction. And Wigner-Eckhart theorem and all that stuff, if we really believe it's a spin 1/2 particle, as we do, then this vector has to be proportional to this vector. All the vector quantities for a simple enough system have to be proportional. I'll take the spin and I'll divide it by h bar over 2, because that's how we normalize a spin 1/2 angular momentum. I'm going to put the Bohr magneton in on the off chance that the argument we just made has some validity, right? We argued what the basic size should be. And then just in case I got it wrong, I'm going to write this, or put a fudge factor in here, which is this mu divided by the Bohr magneton, and that's dimensionless, and we can put in whatever number we want to make it right. Okay, so it's an elaborate way to do it, but I want to focus on this quantity here, and I want to sort of not talk about this so much anymore. And but what I'm really doing when I do that is talking about the magnetic moment scaled in the most natural possible way. Okay, now here's the prediction of the Standard Model. And it's either beautiful or not so beautiful depending on how you like series and things. But here's this magnetic moment in Bohr magnetons. That's what it turns out we can measure, and I'll tell you how we do that. The Bohr magneton, you always measure something in terms of something else, right? A measurement in some sense is dimensionless, right? If I measure this table, I measure it in terms of the feet, the number of feet marked on my ruler and so on. Okay, and so this is in Bohr magnetons. The first term, the leading term for a magnetic moment is not quantum electrodynamics. Well, maybe that's a bit of semantics, but what it is, it's the prediction of the Dirac equation. That's most of the magnetic moment, okay? It's the moment that comes naturally out of the Dirac equation. If you want to call that quantum electrodynamics, I suppose you can. We typically don't. What we call quantum electrodynamics gives us, it's the interaction of basically electrons and light, let's say it that way. But basically it's this series, this asymptotic series, which is an infinite series. And what this is a series in terms of the fine structure constant, which perhaps you know, it's 1 over 4 pi epsilon naught e squared over h bar c. It's approximately equal over 1 to 1 over 137. Now, Feynman famously said that every theorist should put 137 on their office wall to keep them humble, right? Because we have no idea how to calculate the fine structure constant, even though it really sort of sets the scale of not only atomic physics, but life in some sense, you know, chemistry, physics, and so on. Okay, now this alpha is 1 over 137, so when we divide it by pi, which is about 3, that's a couple hundred. So this series should converge pretty nicely, right? It's 1 over a couple hundred squared, cubed, the quadratic, and so on. And then the coefficients here, C2, C4, this is second order, fourth order, sixth order, eighth order, and so on, 10th order. All of these coefficients are what are calculated by theorists, okay? And they've done a magnificent job of evaluating tens of thousands of Feynman diagrams now to do this, okay? When I was a graduate student at the University of Chicago, my famous professor who had written a book assured us that this coefficient could never possibly be calculated. It was just too complicated. Okay? It's now been calculated, and part of it's even been calculated analytically, and we know the next order as well, which has something like 20,000 Feynman diagrams in it, though most of the integrals there have been done numerically. Okay, and then, okay, not only is the Dirac term the leading term, quantum electrodynamics provides these terms, but the hadronic terms, which are also not part of quantum electrodynamics, their contribution is large enough that given our small error bars, okay, it's an important contribution. Okay, and then there's a weak contribution from the weak interaction as well. That turns out to be just smaller than than our error bars, but we wouldn't know that if the theorists couldn't tell us that by evaluating this term, or at least estimating this term to the first order. Okay, and that's of course also a valuable contribution. Now, remarkably, these terms, these first three, are all known exactly. Now, if they're known exactly, why do I put uncertainties in the last two digits here in parentheses? That's because the exact expressions depend on ratios of the lepton masses. And those have to be measured experimentally and put in. But they contribute, I mean, these uncertainties are negligible as far as making a prediction which is comparable in accuracy to our experiment. The uncertainties in these two coefficients, C8 and C10, are due to the, integrating a zillion 12-dimensional integrals using Monte Carlo methods, okay, and estimating the errors on that. Here's the hadronic estimate okay, calculation with its uncertainty, and the weak contribution is a bit smaller. And I should say I had nothing to do with calculating any of this. The theorists that did, they sometimes give really boring talks, but it's you can see pages and pages of Feynman diagrams. But on the other hand, it's a really tour de force to calculate this coefficient analytically, I must say. And they don't get enough credit for that in my view. Okay, now the standard model, well, two things about this expression. Notice that the right way to think about this is if we measure the magnetic moment, somebody else has to measure the fine structure constant before we can do business together. Okay, and so the theory is really a bridge between two measured quantities. Now, that's not traditionally how it's been talked about. Traditionally, what's been talked about is measuring the fine structure constant, plugging it into this side, and predicting the magnetic moment. So this is called the prediction, but the prediction involves a theory and a measurement of the fine structure constant. And that harks back, I think, to the days when the fine structure constant was measured much more precisely than the magnetic moment. That situation has changed rather dramatically. Now, in fact, the way you get the fine structure constant in the tables of fundamental constants that you see in your textbooks, it takes our measurement and assumes this standard model expression is correct and solves for the fine structure constant. Okay, but that's just because we measure it more precisely. Okay. Well, what are you doing, Bill Gates? There we go. Okay, to measure the fine structure constant independently, I don't really have time to talk about that, though I'd like to, because I'd like to give Steve Chu a hard time because he never measured it, okay, the way he promised me once in my living room that he would do. Well, I'm overstating it a bit. But okay, here's how you can measure the fine structure constant. Okay, the fine structure constant is defined here. The Rydberg constant, which you're mostly familiar with here, gives you the structure of the energy levels in the hydrogen atom. If you mix these two things together, then, boy, I'm having trouble here. Microsoft PowerPoint is not responding. Wait for the program to respond. Is that the right answer? Close the program. You know, I'm really embarrassed. Someone told me I shouldn't have bought this Lenovo computer that was built in China, but there's too much military research going on this campus, so they shut me down. Let's see here. I'm sorry. I think this is a first for me. Oh, it's showing up there. I see. Oh, this is great. Plan B. Deathly silent here. I'm sorry, Leo. I'm embarrassing you, I know.
No, absolutely not.
Do I want to recover my document? I have no idea whether I want to recover my document or not. Okay. Yeah, no, I'm going through the steps, actually, but I really do hate that message about do I want to recover my document, but it looks like I'm back, right? Okay. Now I have to sort of blank all of your minds, right? How do they do that in the movies? They push a button and all you, okay. This is the Standard Model's most precise prediction. Oh, this is a different talk, isn't it? No. Okay. All right. What you have to do is you have to measure the Rydberg constant. You have to measure an h over m. And Steve had made some contributions to suggesting how that could be done. And you have to measure some ratios of masses of ions. And if you put all of that together, you can get the fine structure constant, okay? And right now, the weak link of this measurement is the h over m. And the way it works is that in this business, if you make the weakest of a number of measurements, you get the measurement named after you. So it's called the atom recoil measurement. It doesn't seem fair. Okay, the ion ratio guys never get mentioned because they do their job so well that they don't contribute much uncertainty. The Rydberg is so good that Ted Hinch never gets mentioned for measuring this. But okay, but that's how it all has to go together. Okay, I won't talk about that so much other than to say that right now this method of determining the fine structure constant is almost as accurate as within a factor of 3 or 4 of what we can get by assuming that the Standard Model is right and then inverting things, okay? And that's actually much better than the people who did the h over m measurement, Birabin's group in Paris, expected to do, and then sometimes experiments work a little better than what you think. Okay, to give you a graphic idea of the size of these contributions, up here on top is our measurement. All right, this is going to be a long day. Okay, so here's our measurement, the size of the magnetic moment, and the dark part is the error in it. Okay, I just want to give you an idea of how the Standard Model contributions come in. Here's the Dirac contributions, which is dominant, right? Mostly Dirac got it right. Okay, there's the quantum electrodynamics terms. I've put the first through 10th order because those are the ones that we need. Okay, I won't go through the details of these different contributions here, but the uncertainties in these things from the numerical uncertainties are below our experimental error limit right now. The hadronic contribution is above our experimental precision, and I should say we're right now trying to make a measurement which is 10 times more precise and more accurate, okay? It's interesting, when we published our last result, I had a huge quarrel with the referee because he insisted that we put the word precision instead of accuracy in our paper. And I said, well, precision, it means that, I could measure it with a sawed-off ruler, and I could have the precision, and the number would be right. Accuracy, I told him, was what you bet. I said, 1 standard deviation of accuracy is what you bet your yearly salary on. Okay, I thought that would make him convince him, but it didn't. So we compromised. I actually had to change it, and had to change the word to uncertainty to get the paper published, which was a little bizarre. Okay, he's a friend of mine. I know who he is, and I have my eye on him, but okay. All right. So the Standard Model's most precise prediction, if you put the best fine structure constant that's independent of our measurement in, and you use this formula, here's the Standard Model's most precise prediction, here's the uncertainty in the last digits. I don't know all these digits, I don't expect you to, okay? It's just a lot of digits. It's sort of impressive that the Standard Model can predict so many digits, okay? Remember, this is the same Standard Model that I told you last night couldn't predict why we have a universe. It sort of predicts that we wouldn't have a universe, okay? And it can't account for dark energy, dark matter at this point, and so it's got most of its description of reality is wrong in some sense. Okay. Now, how to determine the electron magnetic moment to 3 parts in 10 to the 13. That's our experimental uncertainty so far. That's a little ridiculous, but it's irresistible to an experimenter. If the Standard Model makes such a precise prediction, how can you resist not trying to test it? How can you resist testing it, right? That's sort of the idea here. Okay, and we have a new measurement underway. The most important thing that you need to do these measurements is you need good students and stable funding, right? Good students are even more important than the stable funding, okay? The experiments take longer than usual. This is 20 years and 8 PhD theses. There's been more than that now. And in order to keep this sort of thing going, you have to have a steady output of other results, which also seem interesting enough to the community that they allow you to continue. Okay, the publications come less often, and it's harder, at least for young people, to attract and sustain funding. I hope that our new center will help with that a bit by making this sort of physics more visible. I think that here at Stanford, you have more than your fair share of such physics as well. And so I think you guys pulling together also makes a strong case for this sort of physics. Okay, now here's how you do the measurement. Well, the basic idea, I showed you a picture like this last night. This time there's an electron going around in a 6 Tesla magnetic field, and the classical view is there's a circular motion and it's 150 gigahertz. Not an especially easy frequency to operate at. It's in the microwave microwave range, a wavelength of 2 millimeters, so it's hard to do direct detection and stuff at that frequency. Now, that's not really what we want. We want to make it like an atom. That's sort of like a Rydberg atom, okay? And who wants a Rydberg atom? You want a real atom with energy levels that you care about, okay? But first of all, we have to keep that atom from coming apart. So we put negative charges above and below. And so the particle, when it comes up, is repelled by a like charge, okay? I got that wrong on my slide last night. Okay. All right, and now we don't really want that. We want to make energy levels. So what we do is we cool the motion of this so much, okay, that we sit in the low quantum levels, okay? In fact, we'd like to sit just in the ground state. And then we'd like to put some photons into our system and make it excite to the first excited state. So we do an experiment just like you'd imagine in high school chemistry. You're in the ground state and you put it up to the first excited state. But this isn't a real atom. This is our artificial atom. Why make an artificial atom when God has provided so many perfectly good atoms? Well, the reason is this is kind of a distorted atom. We want it to be, we want it bound so we have a lot of time to make a precise measurement. But what we don't want is we don't want it so tightly bound that when you measure the properties, you're measuring the properties of the atom. You want to measure the properties of the particles themselves. Okay, so you want this weakly bound artificial atom. Okay, now in order to do this and be in the ground state, this is what the electron probability distribution looks like in the ground state. It's really boring. Nothing's going around, right? You know, we call these stationary states, okay, because nothing happens. Okay, and then we want to go up to the first excited state. Now we see this sort of hollowed out distribution of electron as you go off the center axis of this homemade atom. So we'd like to flip back and forth between these two states. Well, first of all, we've got to get the particles in the ground state and get them to stay there. Well, how do we do that? Well, the basic idea is the energy splitting between here, if you'll let me switch to temperature units, so putting in a Boltzmann constant where I need it, this energy is equivalent to 7.2 Kelvin of energy. So in order to get to have the Boltzmann factor put all the probability down here, we have to be at a temperature that's much less than 7 Kelvin. And so that's why we use a dilution refrigerator and we lower our apparatus temperature down to 1/10 of a Kelvin. Okay? Now, you have to think about this maybe to think what it means to have one particle in thermal equilibrium. Right? Thermal equilibrium is usually an ensemble of particles, right? And here we have one particle, okay? So you can think about that for a moment. I'll come back to it in just a moment and give you a quiz, okay? All right, so the quantum measurement that we do, well, if we have one particle and we're in a quantum state, we know that we have these cyclotron energy levels. So I've written the harmonic oscillator energy levels, n plus 1/2. This is the quantum number, h bar times the cyclotron frequency. But of course, this electron also has spin up or spin down with respect to the magnetic field. Okay, and so if I just flip the spin up to spin down, then I get the difference between this with m equals 1/2 and minus 1/2 just gives me h bar omega s. That turns out to be twice times the magnetic moment times the magnetic field. That's not so good that this splitting is proportional to the magnetic field, since the magnetic field isn't perfectly stable. Okay, and so it's going to change as the magnetic field changes in time. The cyclotron energy is, if we change the quantum number by 1, h bar omega c is twice times the Bohr magneton times b. Notice the nifty thing. If we take the ratio of these two frequencies, what we get is the magnetic moment in Bohr magnetons, just what we want. Now, this is perfect for a precise measurement. Okay, because there's nothing in physics that we can measure better than a frequency. Okay, because the art of timekeeping is very well developed. The only thing we can measure better than a frequency is a ratio of frequencies, because now the frequency only has to stay constant during the time we're making one frequency measurement till the next. Right? So this is perfect. So this is the really nice feature of this measurement. Now there's more stuff going on here which I'll sweep under the rug for now. Okay, this is a picture of what our accelerator looks like, our homemade atom looks like. This is the nucleus you're seeing of the homemade atom, right? It's on the outside, right? And one electron sits inside, and it sits there for months at a time. We have good students here, one guy who harasses them, and then lots of apparatus, okay? And, well, maybe I should say what some of this is. This is a dewar, and underneath this floor, there's another dewar that has a 6 Tesla solenoid, to make this strong magnetic field. There's a dilution refrigerator, which is lowered through the ceiling down into this apparatus because it's long and skinny. Okay, so there's lots of technology going on. Okay, now what sorts of things do we see? Well, what I'm showing you here is the energy in the energy that we measure basically in the cyclotron motion over an hour. So each of these slices is 1 hour. Okay, and this vertical scale is energy in units of 0, 1, and 2. Okay, and what I claim is this is a quantum non-demolition measurement of the energy. Now, some of you use quantum non-demolition measurements. It's a common technique now in quantum optics. We've been using it for a lot of years, I think even before the term became popular. Okay, the basic idea of a quantum non-demolition measurement is that when you make a repeated measurement, the measurement itself doesn't change the state that you're measuring. Okay, so you can put something else in, you can do something else, like put some photons in the cavity and then measure it again and see if the state has changed. So the measurement itself isn't going to do your experiment damage. I could talk more about that, but I won't. Okay, so this is, what are we seeing here? Well, we see sort of a ground state. If you look at this long enough, you see a first excited state, and then you see a second excited state, and then you see some little pointy things in between. What are the little pointy things? Well, that's when the particle starts to jump up to the first excited state, but it decays in a time short compared to the averaging time that we need to determine which quantum state we're in. Now, we do have to average for a fraction of a second. It's not so surprising. There's one electron making signal, and there's 10 to the 23, 10 to the 24 electrons making noise. Okay, so you have to exploit the fact that you're narrow band and do some averaging. Now, why do we excite this at all? Well, we're just in a cavity, a small cylindrical cylinder. I'll show you a picture of that in what comes. And basically, that small cylinder makes black body photons because it's at a certain temperature. This is at 4 Kelvin. Let's take this well separated thing. What happens is a black body photon comes in. The system absorbs it, jumps up to the first excited state, and then it jumps down either by emitting a photon by spontaneous emission, or it absorbs, there's a stimulated emission that comes from another black body photon. We don't know which. As we lower the temperature, you can clearly see there are less black body photons in the cavity. So when we get down to 1.6 Kelvin, we only see about one of these transitions per hour. Okay? And here what's happening is undoubtedly a black body photon was absorbed. That made the excitation. And almost certainly, though I can't say positively, this is a spontaneous emission, because on average we'd expect it to be another hour before a black body photon came by to stimulate the emission down. Okay, so and then if you go below 100 millikelvin, then you don't see any transitions at all. Okay, I mean the lifetime there is enormously long. Okay, now if we make a probability factor here, the probability of being in the ground state, the first excited state, and the second excited state, we can extract the temperature. And in fact, the temperature that the electron thinks it's at is the same as the temperature we measure with a temperature sensor, a ruthenium oxide sensor, or a carbon sensor, we use both, on the side of the apparatus, right down to 1.6 Kelvin. Below a tenth of a Kelvin, there's never any transition, so the concept of temperature doesn't even really make any sense. Okay, and temperature doesn't really matter. Now, remember I asked you, what does it mean to be in thermal equilibrium? Well, if you look at any of these traces, clearly you're not in thermal equilibrium. You're in one quantum state or another. It's painfully clear, right? On the other hand, if you take many hours of these, many slices like this, and average them together, then's when you get a Boltzmann factor. Okay, and that Boltzmann factor is the thermal state. So basically we take all this good data we have and we average it all away, because quantum mechanics can't describe what's really going to happen on an event by event basis except in a simulation sort of sense. Okay, now we inhibit spontaneous emission. Well, what does that mean? Well, a particle in a magnetic field of our size will radiate in about a tenth of a second. Tenth of a second is too short for us to average enough to see which quantum state we're in. So what we do is we put this cavity around. The cavity has radiation modes in it. You had to study them from Jackson, TM modes, TE modes, TEM modes, that awful chapter 5 or whatever. I think it's still branded in my brain. Okay, but this is why you have to solve that, because the density of states follows this resonance profile in the cavity. And only on a resonant peak do you have a density of states. So the particle looks out and says, boy, I'd really like to radiate today. But oops, I'm between cavity modes, so there's no density of states. I have to wait a while. Okay? And so we can inhibit spontaneous emission, or enhance it if we want, by tuning the electron frequency to be on or off the resonance with these cavity modes. Okay, and that instead of a tenth of a second, then we get 16 seconds. And how do we measure this? Well, we make a histogram of the amount of time we spend in the excited state. Okay, so that's the basic idea. All right. I don't know what's happening here. Come on, baby, you can do it for me. Oh no. All right, restart the program, close the program. Wait, oh no, here it started again. Okay, I'm going to have to bring this to an early close here. Okay. There's many other tricks that we use in the experiment, and I want to get on to another experiment, so I'm going to stop talking about this experiment pretty quick. But one of the things we do is, I mentioned it last night, we've modified the superconducting solenoid, so when the subway goes by the lab 100 meters away and changes the magnetic field, an extra current gets induced in the solenoid and cancels things out. Things are really a little more complicated in the energy level business, because special relativity is alive and well, so the cyclotron energy levels are not exactly equally spaced. They're equally spaced to within a part in 10 to the 9. Okay, but our measurement precision is much better than that, so we see that they're a part in 10 to the 9 closer as you go up. And then there's two cyclotron ladders because they're spin up and spin down. And for our latest measurement, we started in this state and we either went this direction or went this direction to probe the spin frequency or the cyclotron frequency, and then we got a result. Okay, well, I'm futzing around with this computer too much, so let me just say, the Standard Model's greatest triumph, in my view, is that the theorists are able to use the Standard Model, both the Dirac part, the QED part, the hadronic, and the weak part, to predict this number, and we measure essentially the same thing. Here's the prediction, and here's our measurement right here. Okay, it's about 15 times more precise, more accurate than the result that helped Hans Stehmelk get his Nobel Prize some years ago. So it's 2.8 parts in 10 to the 13. Okay, and now we can determine the fine structure constant by using what we measure and inverting this expression. And if we do that, here's the value that we get compared to the other values. I've already told you this, so there's no real new information here. We get the fine structure constant more precisely, more accurately, in fact, I think, than anyone else, at least if the Standard Model is right. But an important thing is that some of the measurements, the quantum Hall effect and those solid state measurements, the Josephson junction effect that I grew up with thinking as the most precise way to measure the fine structure constant, they don't even come close to fitting on this graph. Okay, they're just so enormously big, the error bars, and some of them aren't even consistent with these measurements. Now, there's a big development that happened in 2012. Here's again our measurement accuracy. Here's the theoretical accuracy as it stood in 2012. This is from the various terms in the QED calculation. And the theorists calculated the 10th order, and that knocked the uncertainty down a lot, which means that if we now measure more precisely, we can determine the fine structure constant more precisely if indeed the Standard Model is correct. And so we hope to do that. Now, this measurement also puts a limit on physics beyond the Standard Model. Okay, physics beyond the Standard Model, here's the argument. Basically, this expression that I showed you, okay, corrections due to the quantum electrodynamics, the hadronic and weak, also new physics. If there's new particles inside of, or if there's particles, ingredient particles in the electron, then one would expect to have a shift. And that's the reason that the proton magnetic moment and the antiproton magnetic moment don't work from this formula, okay? Because there's extra structure going on. And so I don't have time to go for this, but let's just say that the error bars in our experiment essentially establish that the ingredients that are in the electron, if there are some, have a mass, if you pull them all out and set them on the table separately, okay, a mass of about greater than a TeV per c squared. Now, for a particle that's a half MeV, that's a whale of a lot of binding energy, okay? So the electrons that are in our body are really strange particles, right? If they have ingredients, as some of us think they must have, okay, the ingredients, well, there's a whale of a lot of binding energy. Okay, that's all I have to say. 20 million times more than the electron mass. Okay. Just a side thing I won't take. I think we could actually measure the muon magnetic moment in a trap rather than a storage ring, as is being done at Fermilab right now. We're not trying to do it because I don't feel I can do research on one more continent, okay? Because I'm already going to Geneva all the time. But if one of you wants to go to Japan a lot, you can come and talk to me. I have a project for you. Okay. All right, let's, despite the great success of the Standard Model, it can't be the whole story. It can't explain, as I talked about last night, how a matter universe exists. Okay, gravity doesn't fit so well. You can't renormalize it, at least. It can't explain inflation, can't explain dark energy. So the Standard Model is the great frustration, and as well as the great triumph of modern physics. So let me just skip to another measurement that we found irresistible. Okay, we've done lots of different measurements here, so I'm going to skip all of these. Guess we've done too many measurements here. Okay. So we can also test using low energy methods whether proposed improvements to the standard model are right or not by looking for places where the standard model and proposed improvements, like supersymmetric models, are the ones you've all heard of, I think, whether these two things disagree in their predictions. And then we can try and use these low energy methods to see what's right. Now, I've been talking about the magnetic moment, okay, which is proportional to the spin. If the electron has an electric dipole moment, for the non-physicist, that means that the charge distribution is squished a little bit, okay? We should be able to write a similar expression, scaling it as the spin, because that electric dipole moment would also be a vector, and we should look for this constant. Okay? Physicists didn't look for it for many years because it violated two of the sacred symmetries, okay, P and T. I won't go into that. It's sometimes a mistake to be persuaded by your own propaganda, okay, but we're starting to look right now. Okay, the standard model predicts a non-zero electric dipole moment of the electron, but it predicts it in fourth order. Okay, which means the estimated size of that is about 10 to the minus 38 electron charges times centimeters. That's the unit of charge that's always used. Since the measurement, the best measurement when we started was about 10 to the minus 27 centimeters, that's a long way away. 10 orders of magnitude is too much for my optimism even. I think it's going to be hard to measure for a while. The reason is the standard model, to couple in the CP violation you need to have a magnetic moment, has to couple it in via the Kobayashi-Maskawa matrix, and that comes in only at high order. Okay, now the extensions to the standard model, like supersymmetric models, take all the particles and add a bunch of supersymmetric particles, which by coincidence none have been detected so far, okay, which is an unusual situation. Maybe we're going to get a news flash soon that that's changed at the LHC. We all hope so, but let's see. Okay, we formed the Acme collaboration to use low energy methods to try and measure the electron-electric dipole moment. Here's John Doyle, my colleague, Dave DeMille from Yale, and myself. Here's the people who did the real work. A number of them got PhDs for doing this. It was really a very nice crew, and it worked very well together. Some of you know that I was proud until this time, until we got the result, to have never submitted a paper to either Nature or Science. Okay, but my collaborators, the PIs, outvoted me, so we ended up on the cover of Science for this measurement. But how do you measure the electron-electric dipole moment? Well, if you have a Hamiltonian and you have a small electric dipole moment, then you better put a big electric field in there to make some effect that you can see, some frequency shift or energy shift. So if this is small, and no one's detected it so far, so we make this as big as we can. That's the basic idea. Now, an electric field on an electron, that's bad news, right? You'd accelerate the particle right out of the apparatus and the experiment is over. So you can do the experiment with neutrons that way, but not with electrons. So we always do these sorts of experiments within atoms and molecules using the internal field of the atom or molecule as the field which is in the d dot E. So it's the effective electric field dotted into the electric dipole moment. Okay, I won't talk about that. We're using molecules now. I don't like molecules. Shallow famously said here many years ago that a diatomic molecule has at least one atom too many, and that was always my attitude as well. I still sort of feel that way, but the effective electric field inside of our molecule is of order, well, it's a little lower now, but the first estimates were about 100 gigavolts per centimeter. Try and make a field like that in your lab once. It just can't be done. And moreover, you can steer that in the lab by taking just a couple of volts per centimeter field and reversing it, and this molecule and this field obediently changes with you. So it's just a remarkable way to do this. And there are people like Ed Hines from Imperial College who was a pioneer of this sort of thing. My collaborator David DeMille also worked on these in another molecule. It didn't pan out, but he had some good experience there. Now, well, this is a little busy and I'm running a little low on time, so let me just say that for me, I think of this as a two-state system. Okay? If you look enough and you find the right two states, you can find two states which are degenerate. And if you have an electric field and turn it on and there's an electric dipole moment of the electron, one level goes up and the other level goes down. Okay, that's the basic idea. So we're looking for an energy splitting. So that's really simple. The molecule also has a nice thing where the magnetic moment is particularly small because an orbital and spin component cancel each other, which is nice because that way magnetic field fluctuations and stuff are less of a problem. But the energy splitting that you get, and this is an energy splitting that corresponds to the error bar we got in our measurement, is not too big. You know, if you're an particle physicist, high energy physicist, you would say it's 7 times 10 to the minus 30 TeV. Now that's maybe fudging because you put the TeV on here, but if you put it in our units, low energy units, it's 7 times 10 to the minus 18 eV. That's not so many electron volts either. In frequency units, it's 2 millihertz. So you can't just, you know, put a source, a laser source, microwave source, or whatever, and resolve this, because these levels are much too close to each other. So what do? We use standard low temperature, low energy tricks. We make a superposition of these two states. And because they have a slightly different energy, if we let them evolve in an electric and a magnetic field, they're going to pick up a different phase, each of these two states. And then we measure the phase on the other end, and we can control, by controlling the polarization of our laser light, we can control the initial angle, you know, the phase angle in this coherent superposition of the two states. And by detecting properly and changing polarization, we change it every 5 microseconds, we can detect what the polarization is, we can detect what the angle is there and get out this phase. And the part that we're interested in is the part that's proportional to the electric field, the time it takes, the time we let it drift in this sort of amplification region, this drift region, and we can get out the dipole moment. Okay, the basic schematic is the source is made. It's a specialty of the Doyle group to use ablation. Big laser hits a thorium dioxide target and stuff happens. Okay, they claim to understand some of what the stuff happens, but it's kind of a bit of a mess. But out comes some THO. Okay, just thorium monoxide. It goes through some preparation region where we do some rotational cooling. It goes between some electric field plates, which are glass plates, which have tin oxide on them, so we can make an electric field. Okay, we can see these beautiful fringing patterns as we change, you know, these angles between the states. Okay, so we have, if we sit on one of these zero crossings here, then if we put on a little bit of electric field, the phase will go down one direction. If we take off the electric field, the phase will go the other direction. Okay, this will be determined depending on whether or not we have this moment. We can do very fast switches. We switch the direction of the electric field. It turns out in our molecule, we can actually, by changing the laser frequency, we can select 2 states or 2 other states. And those are identical almost, except that the internal direction of the electric field is different. So we do one, then the other, then we subtract. So it's always doing one thing, doing another thing, and subtracting out and looking at the differences. Compared to other measurements like this, we do these switches relatively fast. And that gives us some advantages. Our field is, well, the first estimates were 100 gigavolts per centimeter. There's more recent estimates of 88 gigavolts per centimeter, the effective electric field in the molecule. Theorists have to provide these. It doesn't really matter the differences between here for us, for the limits that we're setting. Okay, but right now it's settled at about 88 in the most recent paper. Here's the result that we had. We were blind to the result, and we did 40 different systematic checks. Okay, very tedious business. And in the end, we sat there with bottles of wine and unblinded ourselves after we had decided to publish. And this was our result. It was consistent with 0, but it was about a factor of 12 more precise than had ever been done before. Okay, now the electron magnetic moment measured in 2002 by the famous measurement of Cummins was at about 2 times 10 to the minus 27. Ed Hines improved it to about by a factor of 2 almost in 2011, and we improved things by a factor of 12, okay, to about the 10 to the minus 28 level. Now, I was telling Peter, if you're in the audience here somewhere, we actually don't measure the electric dipole moment alone. There's also a scalar coupling constant that we determine a limit on. I won't talk about that now, but I'd be happy to after if you want to ask. In terms of particle physics numbers, what do we do? Well, here's the electric dipole moment as a particle physicist would write it. Basically, there's some sort of coupling constant, and the power depends on whether you're coupling to 1 or 2 level diagrams. We do both. We estimate with both. There's the mass of the electron divided by whatever mass scale you think you're investigating. That would typically be the mass scale that the LHC is at, because else they would have seen particles that were lighter than that, we hope. There's some sort of coupling to CP violation with the phase. And when you put this all together, we're probing what we claimed was the 3 TeV or 1 TeV stage. Now, my theoretical colleague said, whoa, why, that should be 10 to 30 TeV. It's because we put a prefactor of 0.1 and just assume nature would be unkind. And apparently in particle theory, you don't do that. You just always assume nature is kind. Okay, so basically this is what we did. We improved things. All of these models here are getting kind of hard to take as seriously as one did before. There are still some models that we haven't excluded. We're working on them. Here's another interesting plot that Feng came up with. I just added some stuff. This is the UW nuclear moment measurement. Here's our measurement. This is a constraint on some of the supersymmetric particles. Notice that we make limits that are far more stringent than what has been possible still at the LHC, and so on. Okay, we're almost done here, so let me just say there are other people doing these measurements. Ed Hines' group continues at Imperial College. At Jilla, they're trying to do a very nice measurement. No result yet. Okay, Penn State and U Texas at Austin, no result yet. Okay. We're in the process now of doing a new measurement, and I'm going to conclude on this note. We're actually taking the data right now, and I'll show you some examples. So if you just take this plot and say, how much better are we going to do, we're going to put it way off the scale now, okay? So we're going to really set by far the highest energy limit. Here's 30 TeV. We're going to be way above that, okay, coming up. And so in terms of this graph, we're going to push it by at least an order of magnitude. Well, what did we do? Well, we improved the molecular flux that we had. Let me just give you a feeling for some of the improvements. To excite the 2 levels in our first generation experiment, we just wanted to get running as soon as possible. We excited a molecular level with a laser. It rained down on 6 different levels, 2 of which we wanted to use. Okay, we blew away all the other population and made a dark state of those 2 levels to have phase coherence. That took away another factor of 2. Extremely inefficient way to excite these 2 levels. Instead, we went to STIRAP, okay, where we did a coherent excitation, okay, of just the 2 levels that we want. That gives us 1 factor, okay, and then there's lots of stable lasers for that. Here's the punchline, though. This is the signal for a molecular pulse that we saw in our first generation experiment. Now, you don't see a pulse here because on the same scale, I put what our new pulse looks like, okay? And it's 400 or 500 times bigger. Okay, here's a log plot, so I can prove to you that there was a pulse under here. Okay, so this is an enormous improvement. We should be able to improve our measurement by at least the square root of 4 or 500, I would say. And this just is hot off the press from last week. This is the phase uncertainty. Remember, in looking at these fringes that we have now compared to what we did in generation 1. This is not an error bar yet because we have to do the systematic studies, and we haven't done that yet. We've looked at the worst systematic that we had last time, and that one we killed. We made it go away. But there's one other now, a new one that's poked up at the new level of sensitivity that we have to understand. Here's the various improvement factors. Okay, it comes out to 500. And then I think in the future, I think there's at least another order of magnitude possibly coming as we switch from an ablation source to a thermochemical source. Okay, here's the summary. Despite a 12-fold improvement, there's no electron EDM yet. That's a little disappointing because, of course, it would have changed our lives if we had found it. Okay, from a scientific point of view, it's probably just as significant one way or another, because we know that some of these models that have been proposed to improve the standard model just aren't correct, and it's important to know that. We're now probing for new physics way above the TeV scale. Okay, it's comparable or higher than the L8C, and the substantial improvement in EDM precision seems possible. In fact, it's demonstrated, so we're plunging on. I would be terribly surprised if over the next year, okay, we aren't able to report at least an order of magnitude improvement on what we had before. And of course, it would be really great to discover that the electron charge is a bit squished, and we'll see if we do. All right, I hope this has given you a little bit of a flavor of these sorts of low energy particle physics experiments. I thank you for your attention.
For a couple of questions. I know some of you may want to escape, but I think some people may also want to hang around for a couple of questions. Anybody?
So what we can learn differently from measuring the neutron electric dipole?
Oh, well, I skipped this. I mean, my computer was giving me trouble. I apologize. I would have gotten to a couple of more slides. I think it's really important to measure the neutron electric dipole moment because the strong interaction, shall we say, contributes to it. There's a much richer possibility, a number of reasons that one could have an electric dipole moment of the neutron than with the electron. The electron, we either have an electric dipole moment from the moment itself or this coupling of the electron to the nucleus. There's about 10 or 11 such parameters, okay, in the neutron case, okay, and that's you're probing different physics. So I think you really want to probe both the electron and the neutron and the proton if you can, okay. Now the neutron people have been doing this a long time, so the increases are not as rapid, though. On paper now, they're looking for factors of 10, or I've even seen 100 claimed. Okay, they're having trouble getting the neutron flux right now, of the cold neutrons that was promised. Okay, so that's a big setback right now. But there's 3 or 4 large collaborations that are working on this. It's considered a priority in nuclear physics.
So can you also play some tricks with neutrons using, I don't know, atoms, molecules to kind of enhance the sensitivity?
Well, there's lots of tricks that you play with neutrons. I'd be happy to talk to you about afterwards. Mostly it's doing the magnetometry, but you have very cold neutrons that you can hold in a bottle, and you can detect their polarization after a long time. I mean, there's lots of tricks in the neutron thing. It's if you don't know about such experiments, it's certainly worth reading about them because they're very delightful. Yeah. Mm-hmm.
There are many electrons in one of those molecules.
Yes.
What does that do to the interpretation?
Yeah, well, that's why you have to be a skilled theorist to calculate this. But what we're actually doing is looking at 2 valence electrons, mostly one, the one on the outside. And then you can correct by adding different configurations to deal with an appropriate level of accuracy for the electrons in the inner shells. Okay, but basically the way to think about it is there's one electron on the outside, and it's in the residual field of the, between the nuclei. Okay, and then we reverse that by reversing the laboratory field and so on. Okay.
What's the QND measurement on the cycle? How do you measure how do you do a quick QND measurement on the cyclotron motion?
How do we do a QND measurement?
On the cyclotron motion.
Yeah, okay. Well, a QND measurement, as you know, but maybe for others to say, if you have a system and a detection system and a coupling, if the coupling commutes with the system Hamiltonian, that's technically then a QND system. And our system is that we're trying to detect frequencies about 200 gigahertz, which is too hard for us, okay? Because it's hard to get really sensitive detectors and stuff for that. And so what we do is we monitor the up and down motion in this trap along the magnetic field direction. Okay, and it turns out that when we flip the spin, or we make a 1 quantum excitation, the effective well of this up and down motion changes because we put a small gradient in the magnetic field, which goes as z, this axis squared. So the magnetic field, a term that is a magnetic moment times the magnetic field, if there's a gradient, will acquire a z squared dependence. That's exactly what the harmonic oscillator has. So basically, then we measure a frequency of an orthogonal motion to learn about which state we're in. And that frequency shifts by parts in 10 to the 8 or something like that, and we're able to resolve that. We have, you know, cryogenically cooled field effect transistors and, you know, stuff like that that we use. Did that answer your question?
Okay, last question?
Was your reference to some news coming out of the LHC regarding supersymmetry just a wish, or is there an actual rumor?
It was very nice to address you, and I have no further comment to make at this time. So, you'll never know. You'll never know.
All right, why don't we thank Gary for a nice talk.
I'm sorry about the problem with the computer.
Talk, but Leo introduced the speaker. So my interactions with Bob Hofstadter started when I was actually a graduate student, and I wasn't a student of Bob's, but near the end of my thesis work, I was working on a completely different experiment than what Bob was involved in, but he came to me and said, you know, you ought to try working on something completely different. And which I did, and I owed Bob, and ever since Bob had me take a left turn or right turn, I'm sure it must have been a left turn. I followed Bob's advice for the last, I don't know how many years, and it's really been wonderful. He turned me into a gamma ray astronomer, and there's a whole lot I can say about that, but I won't. But that whole field, one of the key contributions was Bob Hofstadter. And he got me very interested in that and was very supportive. And I'm very grateful for that. But I think a characteristic of Bob's, and you can read it, I'm not going to read this to you, but there's a history of abbreviated history of Bob's physics career. And what I think impresses me the most is how he was a superb experimentalist. He started out in one field and ended up doing some other things that were completely different. And that's a characteristic that I think we should all be envious of and admire. And I think tonight's speaker will, I think, demonstrate that in many ways. And I think the subject is something of great interest and would have caught Bob's attention. So I'll give this to Leo, and he'll introduce our speaker.
Thank you, Peter. It's a pleasure for me to have this opportunity to welcome Professor Jerry Gabrielse from Harvard University. He really is one of the world leaders in making precise measurement of what we think are the simplest things in nature. What is an electron? What is a proton? And Professor Gabrielse at Harvard has worked many years trying to understand what the structure of these simplest entities in nature is. And I think there's a strong connection with Professor Hofstadter's work, in that Professor Hofstadter's Nobel Prize was for primarily for the work he did on the structure of the proton. And many years later, Professor Gabrielse is still looking at the structure of the proton in different ways by making very, very precise measurements of electron and proton with maybe 13 digits of precision so that you can compare that with fundamental theories. And so he's made I don't know how many world record holding experiments he has on our understanding of the fine structure of the structure of these elementary particles. I was using this fine structure word that's connected to physics, but it's really the detailed structure, electron, proton, and even more, the antimatter equivalents of those. So we will hear in a few minutes, how do you make precise measurements on these little tiny devices? And Professor Gabrielse has made great advances by trapping them and probing them in very careful, precise experiments, precision measurements. He did his undergraduate work at Calvin College. And Calvin College has produced more than its fair share of world-leading scientists. It's remarkable the number of physics professors that have come out of Calvin College. He did his PhD at the University of Chicago, and then I think as a postdoc and faculty member then at University of Washington. And then he was attracted over to Harvard, and he's been at Harvard since '87. He grew up in the Midwest, and he's now sort of in a superposition between Harvard and moving his program to Northwestern University in the next year. I think you once told me you even rode your bicycle from Boston to Chicago. Is this not true? Yes? Okay, so he's headed back to Chicago.
That was a few pounds ago.
Let's see. He's received, by my count, at least 14 prizes and awards, which I won't go into in detail. Member of the National Academy of Sciences, and 2 noteworthy awards from the American Physical Society. His new center at Northwestern University, he's the founding director of the Center for Fundamental Physics at Low Energy. So please join me in welcoming Professor Gabrielse.
Well, thank you, Leo. I guess the introduction kind of calibrates me, right? Only crazy people leave Harvard University, so you have to. That should help lower your expectations for tonight. So, oh, come on in. Are there any members of the Hofstadter family in the? Well, it's good to see you. I didn't actually know your ancestor. I don't know which ancestor it was, but it's an honor to be here. And it sounds like I would have liked him if I did know him, because it sounds like he had a great taste in physics, which means he liked to do the same sorts of things I do. So, okay, I'm going to talk today about setting traps for antimatter. That doesn't sound like a completely reverent physics topic, but I was told that this was supposed to be a not completely reverent physics talk. It was supposed to be kind of a popular science sort of talk, and I'm going to try and make it that. And I do that with some fear and trembling, right? Because, of course, I'm intimidated to be at a place like Stanford where everybody's so smart. And so, you know, you naturally feel when you come here that you should impress everybody here, especially the physicists. And so I'm gonna throw a couple of slides in which are to impress the physicists, okay, just so they take me seriously. But take that in the following spirit. When I went to Harvard, what I learned it's probably different at Stanford, but if you teach a really good course at Harvard, so it's all really clear, then the students tend to say, well, jeepers, that was so clear, we didn't really need to take that class. So what I learned is that at Harvard, and again, I'm sure it's different here, what you have to do in your courses is you have to occasionally blow your students away, right? You have to just say some stuff that they can't possibly understand, and only then will they really respect you. So those of you who aren't physicists, take those slides in that spirit, okay? I'm just treating you in the same coddling way that I would treat a Harvard student. How's that? So this is what my instructions were, and I'm going to try and take them seriously. So I'm going to start right at the beginning and say, what is antimatter? Okay, and some of you know because you're old enough to watch Star Trek. Some of you are too young to have watched Star Trek. So we have to sort of bring the education together here. How does it differ from matter? Is it interesting? Why? And then I think an interesting thing in this sort of context is pure science like this. Is this actually important for the United States? And that may be of the world as well, okay? But America first, I'm trying to... All right, then I'll talk about confining antimatter, and that's where the traps come in. Though maybe you've heard about it in science fiction, right? Because in Star Trek, when the Klingons were coming, then Scotty put more antimatter in the antimatter pod and got really worried when the containment system was breaking down, right? What is all that about? What's the real science behind that? And then talk a little bit about the science that we do with antimatter. And then tomorrow I'll be giving another lecture as part of this series in the physics colloquium. And it'll be more, it will focus more on physics topics, okay? And it will be on measurements using one electron or a few electrons, okay, to test what we call the standard model of particle physics and its most precise predictions. So that will be a different story. So what I'll tell you today is a bit of a 30-year, a bit about a 30-year story, okay? 30 years ago, some friends and I went to CERN, and it was a bit of a bluff, okay? I was a postdoc with no tenure track position, and I had no budgets. The friends who went with me were either students who wanted to work with me or friends who also didn't have permanent jobs. And we persuaded CERN to give us some antiprotons and show that we could trap antiprotons. Now, I would never do that again. I'm much too old now. I would know that I couldn't ever go for a 24-hour trial period and pull off something like that. But I was young and had nothing to lose. We went there, and it actually worked. And that sort of started the story of CERN. I still remember when I went to the first guy's office at CERN, he was the guy who had built the low-energy antiproton ring. And he asked me, they were very proud of this ring, right? They called it LEAR, low energy antiproton ring. And he asked me what energy of particles I would want. And I told him, well, a little lower than yours, about 10 orders of magnitude of energy lower than yours. He decided then I was a crackpot, okay? And so he stood up and started gently escorting me towards the door. And as a particle physicist, he next asked me, what is the luminosity? Now that's the buzzword for how many particles, you know, per second, you know, you're going to get. How many do you need? And, you know, in particle physics, you pride yourself on having the largest possible number for that, right? And when I said, well, in the end, I only need one particle, but I'll probably have to waste a few in order to get there, then he really did usher me out of the door, okay? And so there was kind of a clash of cultures 30 years ago. When he became a good friend once our experiments worked, I must say. He just, you know, there's different cultures in physics and different ways that you approach things. Okay, and as the introduction mentioned, we sort of specialize in using very high precise, very delicate probes rather than very high energy methods which smash things apart. Okay, now CERN has changed completely. They have a dedicated facility. It fills rooms much bigger than this. There's hundreds of people now working on just the sorts of projects that I had suggested when I first went there. And so it's really it's become a big enterprise, right? So this thing has changed. Now there's if you want to read the story of that, I wrote a Scientific American article about what really happened during those 24-hour periods, part of the story that you don't usually see behind the science, but I won't go into more of that now. So what is antimatter? How does it differ from matter? Is it interesting, and if so, why? And is pure antimatter science important to our country and the world, of course? Now, some of you know what antimatter is. It's what lets you go boldly where no one's gone before. Dr. Spock certainly knew what antimatter was. And as I mentioned, Scotty always got worried about the antimatter containment. And as we talk through this lecture, I'll try and help you understand, if you don't already, why the science fiction writers wrote that. How many of you have read or seen Angels and Demons? Okay, now that book is based on the antimatter science that I'm going to tell you about today. You know, Dan Brown also wrote Angels and Demons. So I like to say, also wrote the Da Vinci Code. And I like to say that what Dan Brown did for the Roman Catholic Church in the Da Vinci Code, he did for my science in Angels and Demons, if that helps you understand, okay? Anyway, the story is that thugs go to CERN and steal the trapped antimatter, okay? And we do this at the CERN laboratory in Geneva, Switzerland. And then they bury the trapped antimatter under the Vatican, and they threaten to blow up the cardinals as they meet to choose a new pope. So that's one way that antimatter has made it into our culture. Another way, there's the Hapgood play by Tom Stoppard, has a bearded Russian physicist who pontificates about antimatter in it. This is a more serious work, and my ancestors are Dutch. But I must say that I was once in Moscow and was mistaken for Russian until I made the mistake of speaking. And then once I made the mistake of speaking, I got switched into the tourist line where you pay a lot more money to see the shrines in Red Square. Okay. But this is another place that antimatter shows up. So the question is, how close is the science fiction to the science that we actually do? So let's do the science behind the fiction. Now, we're all made out of matter. And we don't think about this as much as I think we should. But we're all made out of electrons, protons, and neutrons. And if you look around, okay, you know, there's a lot of variety just in this room. And yet we're all made out of the same three particles. Bernie Sanders and Donald Trump are made out of the same three particles. I mean, who could believe that that's actually true? Okay, there's the electron. The electron is, we should annihilate them. Someone's got, okay. The electron is the small particle, and remarkably, the electron, as far as we know, has no size to it. Now, that's incredible. I mean, as an experimental physicist, I just know everything has size, okay? And yet, according to our physics theories, in a real sense, we treat the electron as a particle with no size. How can that be? I would love to be the one to have the group that discovered the size of the electron, though we've not succeeded yet. About 1,836 electrons weigh about as much as a proton. A proton has size and it has ingredients. It has 3 quarks inside. Okay, and that's another story which I won't talk to you about today. The proton is small, but it's very measurable, right? It sets the size of the nucleus, and that's the size of it is. There's, besides the proton, which is positively charged, there's a neutron, which has no charge. Okay, and it has about the same mass as far as we know as the proton, okay? Actually, the neutron's a little heavier, so you have about enough mass so you can take out 1 electron and 1 proton from a neutron. And actually, free neutrons do decay, though neutrons in our bodies don't decay. Isn't that great? I mean, if you think about that, if you had to worry about all your neutrons decaying, you could get a psychosis, right? But fortunately, in bound atoms, that doesn't happen. You know, our reality is just full of these nifty, nifty things. So anyway, matter is what we make out of matter particles, right? You know how to make a hydrogen atom. You take a proton, you put an electron in orbit. Okay, and that's the simplest atom, and then the others are more complicated versions of that, according to people like me, though some of you know better. Okay, and you can add some neutrons to the nucleus, okay, and make the nuclei more or less stable. So this is matter. Now, we're made out of matter. Everything around us is made out of matter. Essentially, everything we see in the universe is made out of matter. So, what is antimatter? Well, to the electron, proton, and the neutron, there are 3 corresponding antimatter particles. This is not science fiction. This is well established in physics beyond any reasonable doubt. Okay, and the positron is the antimatter counterpart of the electron. Now, we called it historically the positron. It could have just as well have been called the anti-electron, right? It would have kept the vocabulary simpler, but maybe it would flow a little less well. Positrons actually do occur very occasionally in our reality. They come out of unstable nuclei when they decay, and there's a source of positrons towards the center of some galaxies, including ours, okay? And we don't know exactly what makes these, but I'm sure there are astronomers in this audience who could explain it much better than I. And then there's the positron and the electron have an opposite sign of charge, okay, and the same mass. Now, those are experimental statements I'm making. In the end, you have to go to reality to find out that that's true. It's not some theorist's imagination that makes it true or not. It's what we measure in reality, okay? And so far as we know, that's true. Now, the antiproton is negatively charged where the proton is positively charged. Okay, and so again, there's an opposite sign of charge and the same mass, so far as we know. I mean, that's been demonstrated to about parts in 10 to the 9, parts in 10 to the 10. Okay, that the mass of these two is the same. The neutron has no charge, so it's oppositely charged to the neutron. The antineutron is oppositely charged to the neutron by a technicality, right? Because -1 times 0 is 1, right? So it all works out, okay? And so these two fit the pattern as well. Now, as far as we know, we could make atoms out of the antimatter particles as well as the matter particles. Because of course, if you think about what holds a hydrogen atom together, there's a positive charge being attracted to a negative charge, the electron and the proton. Now, if we change the sign of both particles and make the antiproton, which is negative, and the positron, which is positive, they still attract each other, and they have the same properties so far as we know. Now, we're actually doing experiments with that. Okay, my team and several others now that have joined us are really trying to look very precisely to see if indeed that's true. Okay, now if you can make atoms, then the question is, we take matter particles, we make matter molecules, matter cells, matter people. Why not a matter universe? Okay, well, we have a matter universe. Let's do it with antimatter. Antimatter particles, antimatter molecules, antimatter cells. Why not an antimatter people and an antimatter universe? That's actually one of the deep questions of physics, I think. That it's kind of surprising that in 2017 we still really don't have an answer to that. Okay, we currently don't know any reason why people and a universe could not be made out of antimatter rather than matter. So that brings up the question: why is it that we have a universe made out of matter? More about that in a moment. Now, how would antimatter people differ from matter people? Okay, well, we can take Gabrielse, who's made out of matter. Okay, and let's compare him to the anti-Gabrielse, okay, made out of antimatter. You religious types, that's not supposed to suggest an antichrist. This is a scientific kind of lecture. Now, would he be smarter, more handsome, less massive? Well, as far as we know, the bad news is that modern physics predicts that Gabrielse and anti-Gabrielse would have exactly the same properties. Well, exactly is a little strong. There is a way to tell matter from antimatter, but it's really, you have to build really a whole big accelerator like CERN in order to do that, okay? Because it's a very subtle difference that you have to exploit in order to tell the difference. So as far as we know, we could have people and the whole universe, in fact, made out of antimatter. Now, the big mystery is, why are people and the universe made out of matter and not antimatter, right? I mean, in science, usually if there's some question like that, that's just staring you right smack in the face, there has to be an answer that will stare you right smack in the face, okay? And I believe there is one, but we just haven't found it yet, okay? And so a lot of what we're trying to do is to try and learn enough about what we call the basic symmetries of our basic description of physics to see if indeed we can get some hints about this. I'll come back to another related mystery in just a moment. Now, what difference will it make if we solve this mystery? Okay, I'm often asked this in popular science talks, and does it make enough difference that the United States should support such pure science? And I think often in physics we don't take on this topic, though I think that we should. Okay, and the first answer is that if whatever solutions to a mystery like this we find change our basic paradigm, our basic view of physics, okay, then big consequences can come out. For example, before the discovery of quantum mechanics, scientists were very satisfied, for the most part, with the classical description. In fact, people made bold statements about how physics was sort of done. Okay, now we have, my cell phone has a zillion transistors in it, right? And quantum mechanics is a really important thing, okay? And we navigate with GPSs. None of that sort of stuff was foreseen. So that's one answer. Another answer is that scientists tend to invent things. And some of us don't worry much about applications. We do pure science. Okay, but even then, we scientists discover and invent things. I can just give some examples here. The first two came from my building at Harvard. Atomic clocks were invented by, well, at least the hydrogen maser was invented by Norman Ramsey and Dan Kleppner. I was privileged to take Norman Ramsey's slot at Harvard when he retired. They never imagined that there would be a global positioning system that would make use of that. In fact, I was driving my Prius, my first Prius one day, and Norman was in the back seat and Dan was sitting next to me, okay? And I said, have you ever seen a GPS? And neither of them had, okay? And I had bought one because I had told my wife that as a friend of these pioneers, I had to buy one. It was my duty to buy one of the first GPSs, right? I mean, geeks make their arguments, right? And my English major wife rolled her eyes and I got my GPS. So I pulled it out and I got to show the inventors of the hydrogen maser that made it possible how a GPS worked. Now, they weren't impressed with the relativistic corrections, general and special relativity and all that stuff. What they were impressed with was Gwynnie. Gwynnie is the lady who lives inside of my GPS and talks to us and gives directions. So we spent the rest of the trip talking about what algorithm Gwynnie was using to make the directions. So, okay, nuclear magnetic resonance. One of the inventors was here at Stanford, of course. Also, Ed Purcell at Harvard. Ed was one of the smartest people I've ever met. And when he was asked once, what is the use of nuclear magnetic resonance? He said, well, it's an esoteric sort of thing. There's really no applications for it. Even someone as smart as Ed didn't realize that every hospital in the world would be trying to buy as many MRI instruments as possible, okay, to image inside of a body without, giving an X-ray dose and so on. The transistor, we could go on at Bell. The laser, make a better light source. Now it's CD players, communications, grocery store checkout. The internet, they're very fond of saying at CERN that they invented it. That's partly true. In my own case, we once found out that the magnetic fields were changing at Harvard badly because the subway was going down the street. And so we were desperate and we invented a kind of solenoid, a kind of coil that made a magnetic field. And this solenoid would just cancel out the fluctuations in the magnetic field. And now that's incorporated into most MRI imaging machines. So these things kind of come. Now, it's kind of hard to sell these things. You don't want to write in your grant application, you should support my research because I might invent something that I didn't anticipate. That doesn't work very well with reviewers. But as a community, okay, that's an important thing. Okay, confining antimatter. The question here is, Scotty did it, can we? Okay, and well, let's talk about this and the challenge of the confinement, okay? Well, yeah, I have to describe annihilation, which some of you know about, but here's a simple example. If we take an electron and we take its antimatter counterpart, the anti-electron that we call the positron, and we let those two collide, and suppose we do it inside of some big bucket or something that's sort of reasonably thick, then what's going to happen is both the electron and the positron completely disappear. We say they annihilate each other. And what we're left with is a little bit of heat in the bucket. Actually, there's some photons that come out which get absorbed by the bucket. But, I mean, basically, the energy is released as heat into the bucket. Okay? And the famous formula that all of you know, and probably some of you, many of you probably even know what it means, but in our culture everybody knows this, but on balance, you know, I'll bet you even our president doesn't know what it means, okay? E equals mc squared, that's to describe this very situation. E is the energy released if you take the mass, okay, and multiply it by the speed of light squared. Now, why the speed of light should be the thing that connects, you know, mass and energy is an interesting question which we won't get into. But basically, you can produce quite a lot of energy. Okay, so but the important point for this lecture is when matter and antimatter come together, they annihilate, they disappear. Now that leads to the second cosmic mystery that I want to refer to. Why do we have not only a universe made out of matter, but why do we have any universe at all? Okay, because according to our current understandings of how the universe came about scientifically, there was a big bang, a big explosion. According to our standard description called the Standard Model of Particle Physics, there should have been essentially equal amounts of matter and antimatter created. There's a symmetry there between matter and antimatter, okay? And now as right away, the matter wouldn't have run into the antimatter so easily because it was at such high energy, right, that there wasn't much interaction time. But as the universe cooled down, the matter and the antimatter particles would run into each other, okay? They would annihilate, and if you had equal amounts to start, you'd have nothing left, okay? And believe it or not, we don't understand the answer to that question, okay? And yeah, so we have what we call a standard explanation. Now this is for those who are physicists here. It's attributed to Sakurai. If we have a violation of CP symmetry, we have violation of baryon number. This we know, but this we see, but there's not nearly enough of it to account for a universe. Violation of baryon number, which we think could happen, but we've never observed. Thermodynamic equilibrium, which we don't like, even in a big bang. Okay, those three things together would explain how our universe could exist. But none of the elements, you know, by themselves work. So it's a big mystery. There's an alternative, which I won't go into here. So now in physics, though, you know, this is considered now a small problem. You know, why the universe exists is a small problem because we have a bigger problem. We don't understand dark energy recently discovered within 120 orders of magnitude, right? So if you're a theoretical physicist, you got to first solve the 120 orders of magnitude before you deal with the small things, like why does the universe exist? The point I'm trying to make here, though, is that even though, you know, at the turn of last century, people thought that physics was about done. Right now, we don't know most of what the matter is in the matter in the universe. We don't know what most of the energy is. And we don't know why the universe exists at all. And we don't know why it's made out of matter rather than antimatter. Aside from that, we understand everything, of course. Okay? So the good news for the young people is there's still plenty of things to do, right? You know, and you'll outlive all of us trying to solve some of these problems. Okay, now, why compare antimatter and matter? Okay, well, if you're going to do a precise measurement, and I'm known, as you heard in the introductions, for doing precise measurements, one of the hardest things sometimes is to decide what is a good precise measurement to do. Okay, the fact that it's precise doesn't make it interesting, right? In fact, if anything, if you were smart, you would figure out how to do a not very precise measurement to really settle whatever issue you're interested in, okay? And so some of us who aren't too smart end up doing these incredibly precise measurements. I mean, the distance between my nose and your nose, we could measure very precisely. It wouldn't make it interesting, okay? And so if we're with matter and antimatter, what are the interesting things to do? Well, these are the big questions. And I guess what we know is that in our standard description of physics, these things we called symmetry, for example, the way matter and antimatter should behave much the same way, this is called CPT symmetry. Okay, those are the buzzwords. I won't describe that in any more detail right now, but you know, there's either something wrong with that or one of the other symmetries we think we understand because we can't answer some of these very basic questions. Okay? Now, that's a big surprise given that tomorrow I'll show how the standard description of physics can also predict things accurately to 12 significant figures. Okay? I'll talk about how we test the most precise prediction we have of any quantity we can measure. So we went and measured it. And by George, our standard description was right. Okay, and against the backdrop that we know it's wrong. I mean, that's the situation that we're in. Okay, so let's talk about annihilation of big objects just for fun. What happens when antimatter and the matter Gabrielse meet? Well, if anti-Gabrielse is made out of antimatter and Gabrielse is made out of matter and they're about to shake hands, what's going to happen? Now, I don't want anybody to complain about ignition methods and stuff like that and getting it all to happen at once. This is just a simple argument. Okay, but let's estimate using E equals mc squared how much energy would be released. Okay, so 100 kilogram anti-Gabrielse, 100 kilogram Gabrielse. I didn't want to say my weight, and this disguises it, okay? And the energy released is equal to the mass that disappears times c squared, so 200 kilograms worth of energy. But let's put it in terms that people with different personalities can understand. For those of you who are thrifty, it's this many kilowatt hours, right? That's the one place our country is smart enough to use the metric system, right? Is in kilowatt hours on our electric bills. That's a lot of kilowatt hours, okay? My house takes about it uses about a kilowatt during the day and less at night, so it's a few kilowatt hours per day. It's the yearly output, this number, of 500 nuclear power plants. Okay, that sort of puts it in perspective. And for those of you who like to blow up things, okay, it's the energy from 4,200 megatons of TNT. Okay, so it's almost enough to make you, give up your body for science, right? If think of all the good you could do, at least in the peaceful applications, except there's a bit of a problem making an anti-Gabrielse. Now, why do science fiction writers find this so attractive? Well, all of the mass turns into energy. Okay, in fact, you get twice as much energy as the mass of the fuel that you put in, but that's really a technicality. It's because you use up some of the fuel tank, right? You have to have an antiproton annihilate with a proton which is in the fuel tank, so you're actually getting, so it's really all the fuel turns into energy. That's a great thing. If you look at an efficiency number, the energy released per the mass of fuel used, and then I multiplied by a c squared here to use Einstein's formula, annihilation is 200% efficient. It's actually 100%. I just explained why I said 200. Nuclear fission and fusion, okay, they're about 0.1% efficient. Chemical fuel is way down there, so naturally that's the one we all use, right? Because that's the least efficient, and we can make the most possible pollutants that way. Okay, so annihilation has about 1,000 times more bang for the gram compared to nuclear fuel. Okay, so that's why science fiction writers are fascinated, right? Because if you want to go to a distant star, you don't want to burn gasoline in your rocket, right? Because you got to drag along a lot of gas stations. Okay, you don't even want to do nuclear fuel because you still have to take a lot of nuclear fuel along. So if you have a shot of returning and bragging to your grandchildren, so the argument goes, then you'd better at least use the most efficient thing. Now, the question is, how much antimatter can we make? So in order to do that, I'm going to tell you how antimatter is made at CERN. You take a very fast proton, okay, any one of the protons inside my body or your body will do, and you smash it into some sort of target, which has protons in it. When they smash together, the quarks get very confused about who their partners are. Okay, it's like a modern marriage, I think. The partners don't always know where, okay. But you create a lot of extra partners, as many as you have energy for, okay, and out of the debris come some antimatter particles. Okay? Now, the problem with this process is you can release about 10 times less energy from complete and efficient use of an antiproton than it takes to make it. right? So that's a really terrible energy source, right? I mean, it would, you know, well, petroleum would be a really terrible energy source if nature hadn't been kind enough to take millions of years and prepare it for us and invite us to waste it, okay? But okay, this would be a really terrible energy source, and you have to have something the size of CERN, you know, some big accelerator. This is a medium-sized international airport, and the CERN laboratory is going under Switzerland here in France here, okay, you know, you need these big facilities to deal with it. But this is how it's made at CERN, and underneath the ground, okay, and there's beautiful surroundings at CERN, beautiful mountains, and then the ugliest buildings you have ever seen, right? They're made out of piling concrete blocks on top of each other, okay? Very Swiss utilitarian architecture there. But anyway, underground, mostly underground, there's all these different rings where there are particles going round and round, nursed, you know, from these collisions. There's various particles. There's positrons, there's electrons, there's protons, there's heavy ions, there's antiprotons. They all go in these different rings, okay? And when they make all the matter they can make, there's not enough antimatter made in the history of the universe, okay, to even weigh on a scale. Okay, that's an important thing. More about that in a moment. So, is antimatter an energy source for the future? Well, certainly not. It takes too much energy to make it. Can you make antimatter weapons? Okay, now, it used to drive me nuts when I was a young physicist. We got a lot of press when we trapped antimatter, right? It was in newspapers, TV, everything, okay? And then, you know, the reporters would do their story, and the end of the story has no morality whatsoever. The last line or two, you can say anything you jolly well please. And they would, after a perfectly reasonable story, they would say, but nobody knows what sort of implications this has for weapons in the future. You know, that kind of line. And it used to drive me nuts, okay? I've changed my tune on that, but I'll explain that later. Antimatter rockets, maybe you could do antimatter rockets someday, because you only have one rocket or something, but it would take, you know, right now we're nowhere close being able to make enough energy. In fact, the problem of this Angels and Demons book, okay, and the movie too, okay, is there was one missing detail. If you took all the antiprotons that have ever been made in the history of the universe and you annihilated them all together, there wouldn't be enough energy release to boil a cup of tea. Now, you see, the moral of the story is clear. The cardinals should study more science, right? And then they wouldn't have worried about this, and Dan Brown wouldn't have gotten rich on this book. Maybe I would have gotten rich instead, but okay. All right. So, now how do we contain and store charged antimatter? If it's going to annihilate, here's where the traps come in. Okay? If we want to set a trap for antimatter, we can't put it in a beaker, that's for sure, because the beaker's made out of matter. We put the antimatter particle in, it annihilates. There's a bit of a problem. So we need to build a bottle without walls. Okay? I'm going to skip this, I think. And here's the basic idea. Okay? I have to teach you two pieces of physics if you don't know it already. One is that charges near a magnet go in circles. Okay, that's one piece of truth. The second piece of truth you probably already know, and that's, oops, I got it wrong. Like charges repel. Okay? Oh, that's embarrassing. Okay. Well, that's been extrapolated to marriages and all sorts of things nowadays, okay? Oh, all right. I'm just trying to see if you're awake. Okay. But anyway, so basically, if you take a charged antimatter particle and you put it near a magnet, the arrow is the direction the compass would point, the direction of the magnetic field, we say. The particle will go in a circle. Now, it can go up or down, right? And there's nothing that keeps it in one place. And so what we do is we put negative charges above and below, and the antiproton is repelled by by those negative charges, because it has a negative charge. That's a trap, okay? So we use batteries, okay, and magnets to make a container that has no walls. That is to say, the particle doesn't ever encounter any matter at all. And so we've held in traps like this, we've held antiproton, okay, for months at a time, okay, and just held them. Now you have to have a nearly perfect vacuum, okay, and that's another story that I won't have time to talk about. Okay, so basically here's the way we trap the antiprotons. They're going to come in here from the left, They're going to be going along the direction of a magnetic field, and then we're going to put negative charges here, but we aren't going to put the negative charges here first. So the antiprotons will crash through this matter. You say, oh, but they'll annihilate. Well, it turns out if you make the matter thin enough, you can pick the right thickness that the particles can get through before there's an appreciable probability of annihilating, okay? And if it's too thick, that won't happen, of course. So they slow down, in fact, in that material. They turn around, and before they get to the end, then we put negative charges on here so they're stuck. Okay? And then for those of you who know about potential wells, this is the same picture in terms of potential wells. For those who don't know about potential wells, you just imagine a sink, right? If I have a sink and I roll a ball into it, and then I flop the wall up, you know, after it's gone in, right? That's a potential well picture of the same thing, at least an analog. So here's what happens. The particles come in, okay? We slam the door shut, and then they oscillate back and forth. Okay, and then what we do is we say, well, let's slow these particles down. Well, you know, it's really easy to slow things down with friction for macroscopic things. It turns out it's really hard to slow things down, okay, if they're microscopic. And especially for elementary particles like these, it's very difficult. So what we do is the following. Well, I don't have a picture here. What we do is we put a cloud of electrons in there. Electrons are the only matter species that when antiprotons hit them won't annihilate. There's no mechanism for them to annihilate, it turns out. Okay? So we put them through the electrons and we slow them down. Now, it's kind of like, since they're 2,000 times lighter, it's kind of like slowing your car, instead of with brakes, by driving it through ping pong balls, right? A room full of ping pong balls. That's not a great way to slow your car down, but if it's the only choice, then it makes it easier to choose it, right? And this is the only matter species that can do it, and so that's why we do it that way. Okay, now there's various ways to detect antimatter. The way I'll talk about here is we listen to the radio, okay? So if we take an antimatter particle and we make it oscillate in a circle, okay, then and we put an antenna nearby and attach an FM radio to it. Now, some of you younger people, this is the old-fashioned kind with a knob that you haven't seen. This was before buttons and displays and stuff, okay? But it's the same thing. So you tune the knob. And if you tune the knob, you get this really boring radio station. It really has a really narrow signal, no modulation on it, so there's no music, no anything. But it tells you the frequency. You can measure how fast it's going around in a magnetic field. Now you can put a proton in that same magnetic field. It oscillates at the same rate. At least that's what our physics theories tell us, except in the opposite direction. You can listen to the same radio and you can compare back and forth to see whether they're the same or different. So that's the way we do those sorts of measurements. Okay, now we've done a lot of different measurements. Here's just a summary of what we've done. Okay, we compared the proton. Well, here's at Berkeley when it was discovered. It was compared to the antiproton. Okay, at a precision of parts in 10 to the 4, which is a fairly high precision. We improved things by almost a factor of 1,000,000, and then our result was confirmed a couple of years ago after a 16-year lag. Okay, and basically the idea is we failed to find any difference between the proton and the antiproton, so our standard description so far is right. Now, we think we can measure it much more precisely still, and so we're going to try and do that. We've compared the gravity of antimatter and matter using something called the gravitational redshift. I think for lack of time, I'm not going to explain that right now, other than to say that by, some of you have heard of, if you take a clock and you raise it up, okay, above the Earth, the gravitational force on it changes. It goes at a different rate. This is well demonstrated. Okay, it's been done with atomic clocks on airplanes, for example, but other contexts as well. Well, that's one way to change the gravitational force. If you take your clock and change it from matter to antimatter, that's another way if gravity is different for matter and antimatter. So we made a matter clock, a proton going round and round, and an antimatter clock, an antiproton going round and round. And by comparing the two, we could set a limit. And gravity is about the same to at least a part per million by this argument. Okay, We've measured the magnet inside of an electron, inside of an antiproton. We did this a couple of years ago to only 4 parts per billion yet. We made a 680-fold improvement in the measurement, which we were quite proud of. But what's even more exciting, we think we can go another factor of 1,000 or 10,000 times more precise and compare the magnet in an antiproton to a proton. Again, the spirit is the same. We're looking to see if nature is going to reveal some secret to us about where these symmetries are violated. Okay, now tomorrow I'll tell you about an electron experiment which does a similar sort of thing but uses a lot of quantum mechanics and other stuff to do this about 10 million times more precisely. Okay, I don't know if we can ever do the proton and antiproton measurement as accurately as we've done the electron, but we can do it a lot more accurately than we've done now. Okay, so now we also can make traps for antimatter atoms, and so I'm going to kind of conclude with a discussion of that. Now, well, first let me give you the reason. If you look in the hydrogen atom, all of you know from high school chemistry that atoms have energy levels, and when the electron pops between one energy level and the other and then comes down, there's photons that come in and come out and that sort of stuff. Okay, and it turns out that if you pop in the hydrogen atom, if you pop the electron up to this 2s state, it lives for about 1/7 of a second, and you can measure this transition exceedingly precisely. Here's the precision that's been done with hydrogen over the years, and there's a ridiculous precision that's been achieved. Okay? What we'd like to do is measure this same transition with antihydrogen and compare it to the hydrogen atom. Again, you see the thing. We're going to take an atom made completely out of matter and compare it to an atom made completely out of antimatter to see if indeed they're the same. Okay, and if they're not, that of course would be a really wonderful thing. Now, we proposed to do this many years ago. At the time, it was I almost didn't publish the idea to do this because at the time people were thinking about doing these only in beams, and so doing it in a trap people thought was kind of weird. It turns out now there's, like I said, a couple hundred people working on it, and you know, the way you can't trap an atom the same way as you trap the particles I've told you about. Okay, right? The charged particles were repelled by like charges, right? And they orbited in the magnetic field. Well, a neutral particle like a hydrogen atom or antihydrogen atom does neither of those two things. Okay, so you can't make a trap that way. You have to do it differently. Now, this isn't how we do it, but I just couldn't resist showing you the movie here. Okay, this is a frog that's in there. And, oh, something went wrong with my graphics here. Anyway, there's a frog suspended in a magnet, and I claim the frog is having fun. I didn't do this experiment, so don't send me your animal hate mail, okay? I claim that the frog may be having a lot of trouble because it's the most free experience he's ever had. He's weightless, after all, so to speak. But you can suspend a frog that way. That's not how we do it with antimatter, but it's a related idea. Okay, and so let me show you basically the idea here. If you put, this is known in atomic physics, if you take 4 current bars, and these long bars here, you know, are meant to be a current going this way, 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 and then you put currents on the ends, it turns out you can make the magnetic field, you know, the size, you know, how much deflection your compass would do, you can make it minimum at the center of this thing. Okay, and it turns out that an atom in the right state will sit in the minimum of a magnetic field. So if we take hydrogen or antihydrogen, we can make a trap without walls, right? Because it's magnets that we're using to suspend this, and we can hold it there. And you can add as many bars as you like, okay, subject to having an even number or something like that. And what we do is we take the traps that we trap protons in, okay, and the traps that we trap positrons in, we move the antiprotons and positrons together, and we put it into one of these Yaffe trap sorts of things, and that captures the antihydrogen atoms, again in a trap without walls. Okay, and that works. Okay, there's 2 collaborations that have done it, our collaboration and another. We managed to get about 5 atoms per trial in there, not very many atoms. Okay, and so we're working hard to get more atoms in the trap right now. But again, the important thing is to have a signal that you can start to optimize. So these sort of traps, this is a different kind of trap, it's technologically challenging. In our new trap, it takes nearly 1,000 amps of current. Okay, that's a fair amount. Okay, it means that there's enough energy stored in this coil that it will destroy the coil. Okay, if anything goes wrong, okay? We need to do this at superconducting wires, only 4 degrees above absolute zero. I mentioned this. We're only millimeters away from electrodes which are at 1 Kelvin, 1 degree above absolute zero. We have to switch it on in just seconds, and we want to switch it off in tens of milliseconds. So there's a lot of technological challenges in that for those of you who know about this. Here's how we did it, is we took the superconducting wire and we buried it in the backside of printed circuit boards, G10, the sort of material that some of you physicists know about. Here's the wires impregnated. And you can see here's various coils and things with trap electrodes inside. And we can make these beautiful pictures. What these are is sort of sync pictures, potential energy pictures. And this shows you the deepest part of our trap is here. And then it gets shallower as you go out. And I don't have time to talk about the configuration right now. But laser-cooled antihydrogen would occupy these 2.5 millikelvin contours here in this octuple trap, and a similar contour in this quadruple trap. The quadruple trap has only 4 current bars, and the octuple current trap has 8. And I don't really have time to talk more about the reasons for that. There's a lot of technology that goes on in these sorts of experiments, and I would love to talk to you about it, but let me just say that there's a lot of machining. When you do this sort of work, you spend a lot of your time being an engineer, okay? Because unless an apparatus like this is engineered really well, it won't work, okay? And so here's where I made probably the biggest blunder of my scientific career. I don't know if this is a good time to mention this, but we had this coil shown here. It's all potted together in epoxy fiberglass. Costs $500,000 to replace, okay? And I said, well, we can get a little more trap depth, a little more deep, make this well a little deeper if we don't use metal to surround this for a vacuum container, but we glue together an epoxy fiberglass vacuum system. And we built 3 full-size prototypes, all of which worked. Then you guessed it, we built the real thing and it didn't work. Okay, and it turned out that with the glue joints on this epoxy, we could never keep this thing inside at an equal enough temperature to avoid straining the joints. And this set us back by a couple of years. One of my worst experiences, I think, in my professional life. And it's especially hard if an old guy like me makes a bad decision and then the young people suffer for it. But we ended up then making it out of titanium, okay, and E-beam welded, you know, 6-7 inches deep inside it. It was really a tour de force, I think. Here's just some pictures of putting it together. In the end, though, we could turn on our second generation Yaffe trap in somewhere between seconds and tens of seconds, okay, which is a good thing because we otherwise would lose the charged particles in the gradient fields because they were changing. We also could remove the current in much less than the 10 minutes of our first trap. In fact, here we can remove it in just 10 milliseconds or so, okay, and so there's been a lot of progress here. Some interesting things happen that might interest the physicists. When you turn off a big current like this, and you turn it off in 10 milliseconds, there's a big inductive kickback, okay? There's a couple of kilovolts, right? So you have to be careful you don't get killed when you do this. And so that's one thing. The other thing is we have these copper electrodes inside that we use for the trap. And even though we put splits in them, in order to keep eddy currents from flowing, there still can be sideways eddy currents. And it turns out that when we dump the trap, we see eddy current heating on temperature sensors, okay, connected to these electrodes. So it's really hard to keep the coupling down. Lots of interesting stuff. I'm not going to tell you about all the lasers we're developing right now, but we're at the situation, at the stage where we have trapped antihydrogen atoms. What we would like to do is laser cool these, okay, even though the laser cooling is not such good laser cooling because the hydrogen atom is not nearly as massive as it should be, so to speak, and the photon has way too much energy, so the cooling limit is only 2.5 millikelvin, okay, but we made 121 nanometers of light at CERN, and that's a new record, I believe, for that sort of thing. Okay, I'm going to conclude here and just say that what I've tried to give you today is some sort of feel for why we do these sorts of experiments and what some of the challenges are, what we spend some of our time doing. Now, you know, I kind of summarized 30 years of work, so I might have skipped a few details, okay? But you know, when you try and, the secret to good teaching is to teach your students honestly, okay? And I've tried to do that, okay? The big questions that we're trying to focus on is, why is the universe made of matter rather than antimatter? We don't know. Why did our matter universe survive annihilation as the universe cooled after the Big Bang? We set traps for antimatter and matter to look for hints of these sort of answers. And then I want to remind you that pure science is the needed fuel for a technological society. So pay your taxes, whatever the Republicans tell you to do this year. So, all right. So.
Time for a few questions.
Is there a path or a roadmap for higher Z antimatter?
Yeah, it's step aside and let something for the younger generation to do. It's hard. I think it could be done, and I think in principle you could sort of redo all of chemistry, I suppose, though it's really hard given the containment problems with antimatter. I don't really see the reason, okay, but that's a matter of taste. For me, if once we look at the simplest particles and the simplest atoms, and we fail to find or do find a symmetry violation compared to what we expect now, that will be enough for me. You can make machines that have deuterons in them, okay? You can make anti-deuterons as well. They also come out of the degree, but in less copious numbers, so you have to have a source with more luminosity. You could do all this stuff. People sometimes talk about it. I'm personally not so interested in it right now, but you know, some young person will quote me on this someday and say that what a dumb advice I gave by saying don't bother to do that, and they'll explain why. But no real serious path, I think, right now is available. Mm-hmm. You'll have to speak up. Yeah.
You mentioned that you're working on doing laser spectroscopy and anti-hydrogen.
Yeah.
Compared to what was done in the Hedge group.
Yeah.
Is there any hope to obtain the same level of accuracy as was done?
Well, hope. Yeah, hope is easy. Of course, there's hope. Realistic expectation. Well, here's the challenge. When Ted does an experiment, right? He has a hydrogen bottle sitting there, right? And he opens the spigot, okay? And almost without doing anything, a little bit of microwave ionization, he makes a density of 10 to the 12 per cubic centimeter, atoms coming out. We're going to be working with a few, okay? That's a big, that flux change, that number is a big hit. Now, having said that, when we started with low energy antiproton physics, then it was at that time, doing an experiment with just one trapped antiproton also seemed fanciful, right? And it took us a decade or so in order to develop all the methods and so forth to do it. In the end, we did just as we hoped, namely we did our very best measurement with one antiproton and one H- atom together in the trap for technical reasons that I didn't take time to talk about. I think that over time, we should be able to do spectroscopy with one or not too many atoms, okay? But we're a long way away from that. The shelving scheme, which you probably know about given the question you asked, is one that should work, okay, with antihydrogen atoms, because you have the 1s2s transition, and then you have a cycling transition, the 1s2p. And so I think there's some hope, but I think, you know, in the end, I hope that we will end up doing spectroscopy with just one atom at a time, but I can't prove to you that that's feasible at this point, okay? And I'll say this, that Ted Hinch has voted with his feet. He's not even trying to do spectroscopy with only one atom, even though I've tried to persuade him many times to do that. He thinks it's much easier, and he's right, to do it with a whole bottle full, so to speak. That's what he prefers.
So it would be interesting at some point also to determine the size of an antihydrogen.
Yeah, well, the size, you know, there's a whole other story about that, but yeah, yeah, sure.
Another question?
You described some of these very precise measurements that seem to confirm certain aspects of the standard model, yet you have these big fundamental questions up here.
Yeah.
So what are the chances that physics, there's some fundamental lack of understanding about something, like there was back in the days of the Michelson-Morley experiment that took an Einstein to explain?
I don't know the answer to that question. Okay, I think it's a valid question to think about. I mean, there's clearly something wrong, right? I mean, there's clearly a lot of stuff we don't understand, and it's not like we don't understand it a little bit. We don't understand it a lot. Okay, so from that I jumped to the conclusion that there's something fundamental we're missing. Now, a lot of physicists like to describe it as we just have to modify the standard model a little bit. Well, maybe that's true. That's as much an article of faith as anything else. We just don't know at this point. So I think it's a very intriguing state of affairs, and I don't know how to answer your question. And I'm not trying to dodge it. I just don't know how to answer it. Yeah.
Well, one more. Well, we've got a couple. Go ahead.
Can you measure the gravitational force on the antihydrogen?
Yeah, I think that it certainly should be easier than with antiprotons, okay, but it's not so easy. The most speculative paper I ever wrote about was called Antihydrogen Gravity, Can We Measure It, or something like that. And it's really hard. I mean, the whole Earth pulling on an antihydrogen atom is like taking one elementary charge 10 centimeters away and pulling on it. So you've got to clear out these electromagnetic forces, right? The electromagnetic force that holds atoms together is so much bigger. So you've got to really be careful about that. There are experiments that, well, we actually measured with the antiproton to a part per million already, a part in 10 to the 6, and showed that the gravity was the same. There's a couple of experiments at CERN right now, part of the same working in the same area, which are aimed at doing gravitational experiments. I don't think they're going to get a part per million accuracy even, because I think they're much harder experiments than that. But you know, you have to be careful about saying what you can and can't do, because you know, as you get into things, sometimes you invent new methods. But the answer is yes, you can. Yes, we have. Can you do it at an interesting level of precision, which might be parts in 10 to the 10 or parts in 10 to the 12? I have no idea how to do that right now, and I don't know of anyone who does.
We'll take one more question. There's one here.
Since matter and antimatter act so similarly, you look up at the...
Can you speak just a little louder? I'm hearing some people.
When you look up at galaxies that are so far away that they'll never interact, how do you know that some of them aren't made out of antimatter?
Yeah, that's a good question. I mean, there have been experiments to look for antimatter coming from space. I think that the basic argument is that there are so many galaxies and so forth that if there were matter and antimatter galaxies, we would be seeing evidence of annihilation happening, and we don't. Okay, the only antimatter evidence we see, well, two things. I think I mentioned that we see positron sources near the center of some galaxies. Okay, there are also some antiprotons made, but it's when cosmic rays come in and hit the nitrogen and oxygen in our atmosphere, and they'll make. But that's a rate that you can estimate and measure, and go deeper in the atmosphere and see what's going on. So I think we believe that there would be evidence of that. Of course, you can't ever say no, but the limit you set is well below the limit, that would explain the imbalance of matter and antimatter in the universe.
Besides, the fact that there aren't any annihilations, is there anything from just looking at a far-off object you could tell if it was matter or antimatter?
No, not that I know of. Okay, like I said, there's only one way to tell. You have to do a CP violation experiment, which takes a very large accelerator. Okay, and that's the only way I know of to tell the difference between matter and antimatter. Okay, and that we can't do from a distance.
Okay, so why don't we thank Professor Gabrielse for a nice talk.